Okay, hello everyone. My name is Jan Brugard, and with me today I have my colleague Ankit Naik. We will
Hi everyone.
be, yeah, yes, we will be presenting some features of SystemModeler today. Right now,
Sys
here I'm
what
flying
is it, Jan?
over
This is not
SystemModeler.
SystemModeler?
No, well, but we'll get back to that. So right now we're flying over Linköping, where our head office is for the SystemModeler development, Lake Roxen. And there's actually a specific reason why I began with this flight. And as Ankit pointed out, it's not really system model we're seeing, but that's what we were going to talk about. But let me just hand this over to Ankit, and he will give you an introduction.
Thank you. Let me share my screen. Yes. Yes. So thank you, Jan. Hi everyone. I am Ankit, uh, applications engineer in the Wolfram SystemModeler team. Uh, Before we begin this presentation on latest features in SystemModeler, for those of you who are new to SystemModeler, I just wanted to give a brief introduction to it. So what is SystemModeler? SystemModeler is basically a modeling and simulation tool that can be used to model dynamic systems. This dynamic systems can range from, let's say, an automobile to something from life sciences, like how does a drug behave in a body, or it can be from like how windmill behaves in case of wind loads, and there is and so many different other domains. In today's presentation, we will take examples from the energy domain, from a business domain, and finally, we will look at some models from the aircraft modeling domain. So before we look into the features, let me open up SystemModeler so that we can start up with a simple example. So people who are new to SystemModeler, this is the modeling interface of SystemModeler, where you can see a canvas with some components in it. So what's happening in this model? Here, we have two different bodies, and this two different bodies are maintained at different temperatures. And there is a heat transfer operating between these two bodies by a body radiation component. So when you model in SystemModeler, you have a library of various of hundreds of pre-built components, which you can easily drag and drop and create such systems. For this example, as you can see in this library, we have different sub-libraries ranging from electrical, mechanics, fluid, and thermal sub-libraries. For this example, I have used the heat transfer library. Let's say you want to add another mode of heat transfer between these two bodies. Let's say you want to add a heat conduction between these two bodies. So what you would do is you would go to this sub-library and drag this heat conductor element to the screen, and then choose the connection line tool and just uh, click the two ports. And now the model is complete. So now just by dragging a component and connecting with the two bodies, you have a model of where you have a heat transfer process where you are transferring heat by conduction and radiation. Let me give it a value, let's say 1. Now my model is ready. The next thing that I want to do is I want to simulate this model and try to see how the heat transfer operates, how the heat transfer happens. So just to let you know, I have given some initial condition to my two bodies. The first heat capacitor is maintained at 20 degrees centigrade, and the second heat capacitor is maintained at 120 degrees centigrade. So to simulate this model, you just have to press the simulate button, which you can see as the play button on the toolbar. Once you click the simulate button, you enter the simulation center view. This is a view where you can explore the values of different variables. For instance, in this model, here you can see how the temperature of the two bodies is changing. So heat capacitor 2.T is cooling, and heat capacitor 1.T is being heated until they reach steady state temperature. In this view, you have access to all the variables present in the components. For instance, the body radiation component has variables like change in temperature, it has the net radiation conductance values, and various and others. Finally, one last thing that I wanted to mention is in this view, you can also test different scenarios. For instance, what would happen if the heat conduction value increases? So let's say you want to have it as 10 watt per Kelvin, and then you can rerun, and then you can see how how it quickly reaches a steady state temperature. So this was a very short introduction to the different interfaces of SystemModeler, the modeling and the simulation interface. I hope this would give you some background so that you can understand when we explain or when we show the new features in SystemModeler. To give you, before we start giving you concrete examples, I wanted to give you an overview of the things that has happened in the last year. So in the last year, we have worked on several new features that that are targeted at reducing your design time, as well as we have added different Wolfram language functions which should help you analyze and quickly design systems. For instance, here I'm looking at the what is new web page of Wolfram SystemModeler, and here you can see the different things that we have worked on. We have worked on how to make the simulation results more interactive, how to work on like how can you quantify your control system response, or how can you automatically create dashboards and various other features. So if you want to have a overview of what are the new things, you can refer to it. In this presentation, we will use 3 different examples, and we will try to cover some of these features. Also, over the last year, we have added different blocks, which are basically customer stories and various workflows. So for instance, we have a blog on how to work with the aircraft library, or how to model software as a service companies and such. And finally, we have also released various new libraries like the aircraft library for industrial users, the college mechanical engineering library for students, and various other libraries. Also, one thing to note is since version 13.2, we have also made our hydraulic and communication libraries like OPC Classic and OPC UA libraries free for all users. So you can so there is no hurdle for our users to try out different new modeling techniques. Okay, so that was a brief overview of what is SystemModeler and like what are the new features and new things that we have been doing. But now let's start into getting something more concrete. And now I will hand it over to Jan, who will give you a cool example from the energy domain. Over to you, Jan.
Thank you, Ankit. So as said, we're going to talk about an example from the energy domain. For those of you that attended the Wolfram Technology Conference this fall, or follow the presentation on sustainable energy yesterday, you saw me presenting an example where we modeled the electric grid of Sweden in a very sort of basic way. We reduced the number of cities in Sweden to 4: Luleå, Sundsvall, Stockholm, and Malmö, and the number of power suppliers to 3: a hydroelectric plant, a nuclear power plant, and a wind power plant. And based on that, we did simulations and forecasting to understand the energy production of Sweden. Of course, in this case, one of the things that when you model this is the connection of how do you get things into model as data. So the wind power, how much that generates, of course, depends on the wind. And that's a pretty nice thing that you can do in SystemModeler. So you can look at, so let me open this in SystemModeler, by the way. There you go. So here we have the model in SystemModeler, and similar to the drag and drop that Ankit just showed, this is drag and drop together just without components. But one thing we can see here is that it has a wind velocity into the wind to the power plant here, and that is actually generated from data from Mathematica using the Wolfram language. So basically, what was done was to query about the wind speed in Mönsterås at a certain date. Here I put October 10. I really don't remember which date it is. And this, of course, are things that you've seen before if you used Mathematica. But the nice thing here is that you can easily use that to connect into a model. Now, this is using data that already exists, historical data, but sometimes you want to forecast something, and a way to do that might be, or you want to create something more intelligent. A way to do that is, of course, to have something that would be an input through a neural net. So I thought I'd show that instead because we have a new workflow for integrating neural networks into the system models. So for that, I made a very small example, simple here. We have an outside temperature that we just generated based on data acquired in Mathematica that goes into a building, and then we have a controller that tries to monitor the air conditioning system. So this is the system. It's really simple. If I look at that, if I would click into this building here, we can see that it has different things like the air conditioner, it has walls, and so on. It also has something here says heat, says load with a parameter heat load. So what that tries to add to the model is some way of saying how much heat load or heating can we expect from things like people in the building or appliances in the building and so on. And in this case, it's done as just some guess value. So let me just simulate that so you see. And by the way, let's go back here. You saw Ankit doing a model with, he started here with these guys here, which are thermal capacitors, right? And change. And this reuses this to get the room inertia, but then it connects it to other systems. So it's more of a multi-domain system that doesn't stick to only thermal modeling. Anyways, let's get this going. The plots you're seeing here are I'll get back to those if my memory doesn't fail me. Okay, so here we see it. What we see here is ambient temperature during one day, 24 hours, and then the room temperature. So we see how it's switching on and off here because it's an on-off controller that basically whenever it goes below a certain value, we start to heat, and whenever it goes under, we start to cool down. And that way we try to maintain the temperature around some desired temperature. In this case, it seems to be 20 degrees Celsius. But now, of course, there might be things like you might be interested in how much energy is spent. Here we can see over that day was 50 kilowatt hours spent for this entire building. And then you can start to play around with things. And here we see something new, something that added from SystemModeler 13.2. We can add things that are similar to the manipulates of Wolfram language, and you actually can generate manipulates from this very easily. I think you will get back to that, right, Ankit? Show how it relates to manipulates in
Yes.
Mathematica. Right, good. So if we look here, we can change things like right now we have a it only has one window, this floor that we're looking at, but we can say put it to the south and then it will change slightly. Apparently this date didn't make substantial difference. And we can slide things here and see how would the different factors change behavior, and that will immediately update the things. Right. So while this Explorer thing is new, one thing I said, what happens if I also said here that we had this constant value that we were trying to give to say this is the heat load from that added from people and so on. But what if we could give a better estimate of that? One way to do that would be to collect data. So let's start here. I import some data from, you see here, machine learning databases. So it's public available databases with different data. And in this case, we have some data here with columns x1, x2 to y2. Doesn't say what it is here, but there's documentation telling us what it is. So we read this data into Mathematica, right? And then we want to process this data in some way. So you saw these x1s, x2s, and so on. Let me just evaluate this entire section. So by reading the documentation, we could see that x1 actually corresponds to relative compactness and so on. So we create these ones, and with a simple rule here, association thread, we will rename this table and we get something more understandable. So the type of data we have here is relative compactness, surface area, wall area, and so on. So different properties of buildings. And this is collected for 1,296 rows, it seemed to be. So 1,296 buildings, I guess, then, to get some statistics. And then once we have these statistics, we can start to do things. Here we're cleaning up the data a bit. Let's skip that. Now what we can do instead is we can use this data and divide it into two different parts. One to train and one to validate our trained neural nets, right? So let's do that. So now we've done that, divided it into that, and we'll then use this to train a neural net. Here we train for 120 seconds. We can set how long time we want to train, and of course, the longer we train, the better we will, better result we will get. So we have the data here for the net, the train data, and then out here comes something showing how close we are, how big of a, how big of an error we have. So how close are we to actually getting something that is working fine in predicting, in this case, the total energy from produced or power produced by people in buildings, depending on properties of that building. So we sort of try to, properties of the building, use that to predict how much we can expect from surrounding heating. So we do that. Let me stop that. Like 120 seconds is a bit too long. So, okay, so now when we stop that, will take the value, whatever it came to here, will be our trained data. So we have a trained neural net. And now to the new thing in SystemModeler. So what you can do now is first I'll extract the neural net that we trained here. I just call that fnet. So we have this net chain here. And with create system model, the functions you have previously been able to use, for instance, to create models from state space models, from equations and so on in Mathematica, and generate system modeler models from that. Now it accepts neural nets. So we add this fnet. We will create something called mynet, and then we say where to place associated files. So I shift enter here. And get my net produced. So now I have a trained net that predicts, based on some factors, it predicts this power load that we would like to use in our model. So let's see here if it wants to scroll down. No. So let's do it this way then. Go directly here. So here we have the model that I started with, but I prepared a bit. So I prepared it so I can switch here. I can redeclare this from where I use this guesstimate of the power. I will now use the neural net instead. So I changed here neural net, and you will see that the icon changes. However, if I open this, we can see that something is missing here. We have the same model as before. And remember, here we had just an input, a constant input that went directly here. Now what I will add here is this mynet that we just produced. Just like that. Right? So now I can connect this. So we'll connect that one. And we connect this one. So now we have, based on some properties, you can see here relative compactness, surface area, wall area, that you can set as a user here. It will use this neural net to predict your heat power factor from people and other appliances, other things that might heat up, add heat to your building. And we can see those parameters here. But let me just simulate this again. But let's do this. Let's keep this first. I pin this so we don't overwrite it. And then we'll go back to this model here. So now this model, if I double click here, you can see that now we have this neural net in it. So let's go back and simulate. And now with the values, it actually gives the exact same results because I set it up with the estimated thing that happened to be corresponding to my standard settings here for the model. But now suddenly things like surface area and roof area are actually included not only in the model of the house, but in the prediction of this added load. So when I start to play around here, it's no longer exactly the same. So let's change this to north. Let's perhaps do this. Yeah, we'll do that later. So, and we change the roof area, make that smaller, surface area of the house, make that smaller, and we'll give slightly different behavior. In all cases, we can see that the controller or the AC system manages to keep our temperature around the value you want. But it actually behaves slightly different depending on the settings. But perhaps that's easier to see if we look at the cumulative energy in kilowatt hours. So here we have whatever it cost in this case. And if I go over to this pin version and I put that on top, we can see that the previous version cost a lot more. So this way we can now compare and see, start to change. Let's say now that we changed the surface area here. And let's do this. Oh, that was the old one. We should do this on this one, sorry, where it actually has more. So that you saw that on the old model didn't make much of an effect. On this one, instead, it should sort of hopefully have more effect. Then you see that sort of it separates more here between them. Good. So this is a pretty nice way to combine your more deterministic physics-based models with neural nets and expand the use of your, or expand the scope of your models. There are plenty of material that we'll post to you for additional resources on this. But with that, I'll leave it over again to Ankit, who will talk a bit about software as a system and how you can model something like that.
Thank you, Jan. As you said, like you showed a nice example based on physics, but is it is it a requirement that we need? We can only model models based on physics, or we can also model social systems or various other kind of systems? And the answer is yes. We can model different types of systems, like we can model the various business processes or and other social systems. And to do that, uh, uh, for explaining this example on software as a service, I will use the business simulation library. To give a brief background, like how, or before I go to the main example, I want to take a detour and try to come up with a very simple example of how you can use. Oh, hi.
Can I stop
Yes.
you a bit there? Can you zoom in a bit on that image, because it's very small?
Oh, okay. Yes. Is this fine now?
Yes, that's better. Then I think people can see.
Thank you.
Yeah.
So yeah. So here's a simple example from this domain. Let's say you are starting a manufacturing company and you want to figure out, like, as you start building up your company, how much inventory you're going to have, and you want to understand so that you can find a warehouse where you can store those inventories. So for a process that you have not started, you want to model how things would look like. And here is this example, this model of a simple production chain where you have something called a producing block, through which you give a production rate, and then you store it in a component called inventory. From this inventory, you have a, uh, purchase profile, and this purchase profile ships the inventory to your customer. And then your product has, let's say, a life of 5 years, after which it is scrapped and it goes to the scrapyard. So here is a simple production chain of a product, how it starts, how it's being produced, shipped, and scrapped. Using this model, then you can simulate it, let's say for, I've simulated for 60 months. And here you can see, let me zoom in, yes. So here you can see the blue curve shows how over the given span of time, the installed base is like how many products you have shipped to your customers. And here you can see how is the inventory level changing over time. So as you start building upon your inventories, and you can say that when everything is stable, you reach a constant inventory of, let's say, 1,200 or 500 products. So by this way, you can test different purchase profile, or you can try to model a market demand, and you can try to see how the inventory profile is changing, and then you can plan for your warehouse accordingly. And in this plot is basically the different demands and different rates I have used to model that. As you can see, the production was constant, and here for initial years I was not shipping, and then I gradually started shipping, and after which I reached a steady rate. And here is the scrapping thing, right? So, and to do this kind of models in the business simulation library has various components that help that you can directly use. So it's not something that you have to start making your custom components. You can directly readily use the built-in components from there. And here you have the examples package, where you can see there are examples like production chain, at the SIR model, or love-hate dynamics, Lotka Volterra systems, which is a very popular system in system dynamics. So there are various examples in this library that you can use as template and build upon your different processes.
So those that you mentioned here seem like to be quite small examples, but I assume you can do you have
Yes.
examples of larger stuff, right?
Yes, and now comes to my
Okay,
software as a
sorry.
service company. So just to give background, Jan, of how I started with this model, I was watching Shark Tank, and uh, I heard terms like, okay, growth rate, a company's making losses, and people are projecting like how much marketing expense do you have. So there were so many different terms when I was looking at this show, and then
And
I
for
thought,
anyone joining from the UK, when he said Shark Tank, he actually means Dragon's Den, and that's what it's named.
yes. So I thought, okay, this is a very dynamic process, and like, why not model this process of a company, and try to see how those numbers give us some indication of the different trends of what would happen in the future. And from that question, I started modeling the entire process. So this is the top level view of the model, uh, where you have but it has different components, but I will not go into all the components. For instance, it has this flow of customer journey, and I will go into more detail into this. But it also has a block on product development of a software, like how does the number of employees affect the product development, or how does the morale among the employees, it affects how quickly a product is being developed, and so on. But for now, let me just try to explain the most important or the part that I like the most, and it's the customer journey, which was really new to me. So here uh, you can see different components like unaware customer, aware customer, trial users. What is this? So uh, this is something called as a sales funnel. Let's say you want to start your own company. And for your company, once you have a product, there is a target group who are completely unaware that you have created this amazing product. So you start with a target group of, let's say, 10 million customers who are completely unaware. To reach those customers, you would then have Facebook ads, you would have ads in billboards and various other ads. And through these ads, you want your target audience to be aware of the product. So here you're moving your unaware customer to an aware customer stage. And once someone knows about your product, they will not directly try it. You have to show them some blocks, some use cases, you have to show them more resources so that they are more inclined to try your product. So then you make the aware customer a trial customer. And when you become a trial customer, there will be a group of audience who really like your product, and they would pay once and become occasional users. There will also be a loss of customers at this stage, but but I have not shown it in this snippet. And from occasional customers, there will be some customers who really love your product, who really see the value in your product, and they become repeat customers. So, and this is how the simulation result looks like. And this is for a span of 10 years. And you can see that nothing happens until year one because you have no money to spend on advertisement. So theoretically, nobody knows about your product. That's why nothing interesting happens up to year one. And after that, you can see that suddenly people are becoming more aware of your product. And since you have a very nice examples, blocks in place, you're trying to convert a lot of aware customers to trial users. And here is the final thing that gives you money. And that's like how many you could convert to occasional customers and repeat customers. The difference being, if you have a repeat customer, you gain more. And if you have an occasional customer, you gain less. But so this was the you could say how a sales funnel works like. But of course, my model is much more than that. Uh, Let me just simulate this model and try to see what are the different scenarios I have stored up so that we can test different like different strategies. So once I simulate this model, I will just have it at 10 years. So, and I will just give it some design. So it's better to see. So Jan has already introduced you slightly to this new thing. It's the control panels. So as my model was a bit complex, it has like hundreds of different parameters. And when you share your models with someone else, you don't want your users to be bogged down with so many different parameters and plots. You want them to give a minimal view so that it's very easy for them to interact with. And that's why we use this explore panel. And it has different control panels like advertising, product pricing, and employees. Let's open the product pricing panel. And here, let's try to, okay, I keep on switching. Yes. So now, once we have this model, let's try to test a strategy. So here, let's say one of the questions that comes is, how would a product be priced so that you get the maximum profit or you reach breakdown very fast? That's a question which people ask. And
Or break even, I guess.
yeah, or break even. It's a question which people ask, and everyone has a different answer to it. And I was like, okay, but what is the process? Like, what is the process that you are basing your decision on? So then let's look at this process. So for my model, let's say if I have a price of 100, I have used a unit of sharks in this case. So if I have a constant price of 100 sharks, and if I simulate my model, you can see that at around 7 years, I am reaching the break even. And at the end of 10 years, I have around 103,000 customers. Let's try a different strategy, which you can see a lot of software as a service company do. Like they start selling you the product for free. And after a few years, they put a price on the product. Let's try to see how that scenario would look. So let's say I have a minimal uh, uh, price of 10 sharks. And then after, let's say, 3 years, I increase the price, let's say again to 100, uh, 100 sharks. So let's see what happens here. So here you can see that initially you are making loss, but at the third year, you start to break even. And why so? The reason being, as you had a very small uh, price at the start, you were able to reach a lot of customers. A lot of people tried your product, and the assumption is that they were hooked by your product. And when you charged a price for it, they were so hooked that they were not able to move on. Of course, there are some people which you have lost. That's why you don't have a constant curve. There's a discontinuity here because you are losing a lot of customers as well. But still, people have actually tried your product and they see that there is a value in your product, and you can see with this, even if the rate of increase in customers is slow, you have attained break even and you have around 200,000 customers at the end. So this is a at least this is a good insight to start thinking about how you should price your product. This is not the only way you should do it, but it shows your trend and it gives your thoughts some numeric values. You can quantitatively use this kind of methodology to design. Finally, let's say you have this beautiful model in SystemModeler, but you want to share your model with various other users, your friends, and they don't have SystemModeler, but they do have the desktop version of Mathematica. So, so in the last release cycles, we have worked upon this resource function called SystemModel manipulate, which, as you can see, automatically uses the control panels that you have stored in your model. This is the advertising, and let me get back to the pricing. So here you can see you have a nice manipulate with all the data from the control panels. And then this one you can easily share with others, like just by a single line of code where you're just defining the model name. And it's become so easy for your users to get insight from it. Right, I think I'm taking a lot of time, Jan. So I will quickly finish by pointing you to some good learning resources. Like we have a blog exactly on this model, which came up like 1 week or 2 week back, which you can refer if you want to know more about it. All the models, they are shared from that blog. And also there are various presentations on this way of modeling, which is called system dynamics. And there are various presentations and examples which you can refer to learn more about it. And of course, if you have any question, feel free to drop us a mail. That's fine. But
or
enough.
ask at the moment, as people are actually asking at the moment, and we
Oh,
will, after
okay.
my part, we will be answering together on those questions. So keep on asking
Yes.
in the chat.
Nice. Okay. Now to answer the question that Jan, to answer my question that Jan started with, like, what was that, Jan? Like, how are you playing with this aircraft thing? Can you tell us more about it?
Yep. So let's go back to my screen here. There you go. Now you should see my screen. And let's go from software as a service to aircraft. But yes, before we do that, yes, the reminder, keep posting questions. We will answer them after this section of the aircraft. And then also, as you saw, we have references and so on in the notebook. This notebook will be posted for you so you will be linked from YouTube to a community post where you can get the whole notebook and get all the information afterwards. Anyway, so let's look at the aircraft library. I started to fly around there using actually this joystick. So the nice thing with developing models is that you can play a bit also, right? And to give a bit of introduction to this, this fall we released a new library for aircraft modeling. The models can include things like aerodynamics, forces, and both locally on the different surfaces as well as other properties. And the idea with it is to make it easy to do quick testings of both completely new concepts, new designs, but also alterations of designs that you might be doing. So, for instance, if you're looking into developing an electric aircraft at the moment, you would like to test that and see its performance. So that's the basic idea behind the library. But let me start with this example here. Perhaps increase that a bit, I guess. Something like that. Is this scenario here we have says Pipistrel Alpha Electro. Pipistrel Alpha Electro is an electric aircraft, and here over we can see another aircraft, Schweitzer SGS 136. That's a quite old aircraft and very different because it's a glider. So what we'll be doing is towing this aircraft with this towing rope here. And they are both controlled by some autopilots here. Let me just go from there and look at this model in the library actually. So let's see here. Examples, and I'm starting to open the library here. You see there are a few examples, and here's the glider tow. So open that here, and you see the same things. If I go in and click on one of these, you can see there's a bunch of tabs. There's tons of things you can set to get the exact properties of your aircraft. There are those pre-designed, like the Pipistrel, that you can just use. It's ready set up and parameterized. But if you want to make your own, you can parameterize and you can change it sort of as you want. You can change engines, you can change propulsion system, the propulsion system as a whole, with from electrical to electrical, from turboprop and so on. But let's just simulate this. And of course, while this is simulating, let's actually, oh sorry, go back here. We'll go back into question, because one of the questions we got in the early presentation was on control system design and how you design controller, and of course that relates to the autopilots. And here we have an autopilot, and we see it has a bunch of PID controllers to control the commands for the throttle and rudder and so on. And in comes things like the commanded altitude, velocity, and so on. So the question was, how do we design this? And I'll give this to you as an exercise, Ankit, to after this presentation show something to show a bit about control design and mathematics. So I hope you can do that. That was kind of me, right?
Yes.
Anyways, let's this. Okay, so it's running a bit slower now when we have the Zoom session running at the same time. So that was odd. I guess that's the reason. But there you go. Now it will start simulating. Let me under until it's done. Zoom consumes a bit too much power every now and then. Show a bit more about the library. So we have here. It says physical, and it says state space. So traditionally, if you use traditional tools, you would have state space representations of your aircrafts when modeling. However, the problem with the state space representation is that you have a linearized version that will not give you full the full correct physical properties of the aircraft. So the state space part here are made as a reference more of to legacy models, how they were used to be made before. The physical models here, they are more traditional models from as we typically do in SystemModeler with the actual equations. So if we go in here, we can see there's a fixed wing package, and that package will have, for instance, the Boeing 737, which happened to be the one I started flying there with flight gear. So if I open this, I can then see that it has propulsion surfaces, body, and I can go in and look at, okay, how is the propulsion made? in this case, it has 2 engines. You can sort of see by the grayed out here is made so you can configure and activate more engines if you like, or just make it with 1 engine and see how that would perform. You can switch the engine types. So let's see if let's go propulsion here. You can see that it says, okay, is it wing mounted and or not? So basically, how are the engines mounted to our aircraft? Sorry for that. So on. So great. So that's the way it's built up. So it's built up as any other library that you used in SystemModeler before. Yes, it happens to be aircrafts. Here you go. Here we have the simulation done for 25 minutes. If we look at the curves here, we see that a red and an orange one here. And we see that there are different things on top here because we have actually the reference altitude and the actual altitude. So you can see here, if you look closely, let me just zoom into that part. We can see that there's a deviation between the reference altitude and the actual altitude of, in this case, the glider. So just as anything else here, you would be able to go around and test around. And again, you can see these control panels where we can change things. In this case, it's set up to change the release height for the glider and tone rope length and so on. But let's not go too much into details here. Instead, I'll open the visualization as it's seen in the SystemModeler. So here we have the 2 aircraft, and rather than actually running the simulation real time, let me just pull you through here in some bits faster speed. So you see here, it's towing the aircraft, and what we can see meanwhile is that the actual forces acting on different surfaces are illustrated. This is, of course, something you can turn on and off as you like, but it shows the lift forces and so on your aircraft. And then let's proceed here. It seems like nothing is happening, and it's because we locked into the glider and it's just going steady. But here we see now something starts happening. So let's play from here. So now we see that the glider is released and we start flying around, just gliding in the middle of air. Right. And that's the way a traditional simulation in SystemModeler would look like when you animate, right? So it's a rather simple animation environment because it's not a game we're producing. We're doing this to illustrate things like the forces here. So why did I start with something with a completely different looks, with flight gear? Well, the thing is, once you produce one of these, you can use that and connect to different things. In the case I did in the beginning, I actually used the system model, and I can show which system model I used. I used, let's go here and find this one here, Boeing 737. I used this model here, where you see joystick input and some very simple logic to interpret the signals from the joystick. That goes into the autopilot. The autopilot then sends information to the aircraft that will be controlled accordingly, fly accordingly. Of course, that is fed back into the autopilot, its position and so on. So the autopilot knows how to handle that and so on. Once you've done that, and here you can see the trick here, it has something called FDMTX1. That's actually a block that we added here to connect it to flight gear. So now flight gear, when I run flight gear as I did in the beginning, I shut it down now, so I won't open it again. So when I run flight gear and SystemModeler at the same time, it will just fly accordingly whatever I do in this model. So what we were visualizing in flight gear was the actual simulation of SystemModeler. And if you want to see what we actually what I was actually doing, I can go, this was the simulation that ran when we saw the flight care stuff. So you might remember this from early on in the presentation that you got a quick view of this. Here you have whatever I did with a joystick. So I started to move around a bit here, trying to show you Linköping. And then after a while, I released it and started talking a bit with Ankit, if I remember correctly. But then you can go and see the different things. Like if I double click here, okay, that was zoomed into a very, as I stopped the simulation beforehand. I can see things like, in this case, throttle position for it and so on. But I can see fuel consumption and different things. So this way, it's not only a game sort of model developed for a game engine. It's actually something that you can draw real conclusions for when designing an aircraft. So with that, I think I'll leave over to you again, Ankit, and yeah, or let me just remind you again that we have a Learn More section with things here that you can download to get more resources of different kinds. But with that, I'll leave over for you again, Ankit, and give you the question about control design and how that would be made.
Right. Okay, let me try to answer it. So over the past few releases, we have been working on improving the workflows, like how would you use a model and Mathematica together to quickly come up with initially a first tuned version of your model. So there are various examples, but I will try to explain or show you an example of a model predictive control that was released in 13.2. So now let's say here I have my control problem is I want to control the speed of a DC motor.
Can you zoom in a bit?
Yes. Yes, is this fine? Or
yeah, I think so.
Yeah,
I think that's fine. Yeah.
Yeah. Okay. So here, so what let's say I want to control the speed of this DC motor. So I start by modeling a simple like electromechanical model of a DC motor, as you can see here. Once I have this model, as you all know that in order to work with control systems, a lot of the theory is based upon a linearized model. So the model that we create is a nonlinear model, but what we do is we linearize the model about the initial position or about any operating point or equilibrium point. In this case, I'm linearizing my DC motor about the initial point, and you can see the state space representation at that instant. And once I have that, then I give some specifications, like I give a sampling period, and I give like what is the output that I want to track. In this case, W, which means the speed of the DC motor. And since it's a predictive control, I also need to give a time horizon. In this case, I've given a time horizon of 3, which means you predict for 3 future steps. Then in the next step, you again rectify yourself and update the control logic. And the good thing with MPC control is you can actually give constraints, which is really important, because sometimes you end up giving too high input and some of the physical constraints are not followed. For instance, I want to control the amount of current that is flowing in my circuit. So I give it a range like 0 to 1 ampere. And then we have this new model predictive controller function where you just specify the specification, the model, and the constraint. And what it does is it gives you the MPC controller, the first version of the MPC controller, and then you can use a connect system model controller to automatically connect your controller with the plant. So with this function, you get a controlled system. And once you use a control system, in this step, what I've done is I'm given it a reference signal, and let's see how the system behaves. So here you can see the blue line shows the actual velocity, and one is the reference that I've given. Initially, my shaft was at rest, so it starts with 0, and I give it a reference of 1 radian per second, and you can see how uh, the speed is attaining the reference speed here. And then you can so this shows that the model is able to attain the reference speed, but what about the current? So once you plot this current, you can see that the value of the current is like 0.04 for my toy example here. So you can see that it's below 1 ampere and above 0. So it's respecting my constraints. And one new thing that we have also added in the last release is once you when you are working with control systems, you have to work with different control philosophies or different control logic. And the thing is, once you test a control logic, you want to compare two different control logics. And to easily compare that, you need some parameters, some performance parameters for a logic. So we have this new system model measurements, which gives you this performance parameters. For instance, in my previous curve, like here you can see the settling time of 30 seconds. So my system settled down at 28.6 seconds. And also there was an overshoot of 10.7%. For some systems, it might be tolerable. For some systems, it might not be tolerable. So if you want to compare two different control logic, you can quickly do that using this new system model measurements function. But this was on MPC. If you are working on, we also have examples, which you can find it out in our web page, where if you are working on pole placement philosophy, then we have this hovering control of a submarine, which is working like a regulator. You're trying to maintain it at a constant position. And here you can see that we have used the state feedback gains
Now this is
function.
very small.
Okay. Yes, thank you for reminding me. So then you have this state feedback gains thing where you can use the pole placement control design philosophy, and then you can use the same connect system model controller to give you a controlled system, and then you can see uh, how an uncontrolled system would behave, and the orange one how a controlled system would behave. Similarly,
So,
if
so in general, we have other questions too here
sorry.
to get during time. So, if I would summarize this a bit, is that there are different ways to do the controllers, and there will be linked examples to that. And this is one thing. We're also adding new features all the time on the control design and optimizing it more and more for you, so it should be as smooth and simple as possible. And typically, well, that part you have the system model developed in SystemModeler, and then you do the control design in the Wolfram language, as you saw here in the examples. If you keep sharing here, I'll see the questions, some of the questions here, Ankit. And okay, so there's one here that I think I can answer directly. It's on somebody thought it was nice to see discontinuities getting modeled, and then asking if these variables can be integer based, and yes, they can. So nothing such a fractional number. Yes, you can, and I don't know if you already happen to have an example with that. You can Ankit or not.
Uh, for business case, I don't have an example right away.
Not for
You
any case. But anyway, so let's just say it does work. We can post the examples of that afterwards. You can even do, let's say, enumerations rather than referring to. So rather than having 1, 2, 3, they will be called. Yeah, you could see the north, south, west that I had in my model. That actually corresponds to integer values 4, 3, 2, 1 in some order. So that's actually integer values representing that in the model. but they are then enumerated with some name that is more easily recognizable for you as a user.
Right.
We have also a question in finance related. That perhaps is something you can
Yes.
answer. You've seen that on time for value of money, interest calculation,
Yes.
so on.
Yes. I don't have an example, but I do have a component. Uh, So here in the business simulation library, you have information processing sub-library, which has the various financial related terms like calculating present value, time value of money, trend-based forecast. So these are the things which can help you in discounting and all those time-related things.
And you said you were using sharks in your model, so I assume that means that you created that as your own unit in the model and then use that, right?
Yes, yes. So I used a custom unit
Yeah.
for
So
my
so
case.
so with that, it is possible to do custom units. So if there is a unit you're missing, then you can define it yourself, and whether that's sharks or dragons or some other unit, you are perfectly welcome to add that to your models, or you use built-in SI units and other units. Where can I get resources for getting started with multi-body modeling? That would be Wolfram U. I assume is the best place to start, right, Ankit?
Uh, yes, Wolfram U is a good place to start. But from my personal experience, if you want to start with multi-body modeling, I would recommend that you start with the planar mechanics library, because if you start working with multi-body directly, it's a three-dimensional thing. So there are a lot of there is one more dimension to it, so it makes it a bit complicated. I would recommend start playing with planar mechanics, so that, and it's uses the same philosophy as the multi-body
Right.
library, but it's easy to start, and you will it would be nice transition from this stage to the multi-body stage. That's my experience, but Jan, you might have other experience or other
No,
comments.
the thing is, from back when I learned how to do multi-body, there's a lot more and better resources than back then. But
Okay.
again, can you show how to get to Wolfram U? I think we
Yes,
actually have that
I will just
in the
do.
notebook too, but we can just show here. So if you search for
Yes,
Wolfram U, as Ankit did here,
yes,
um,
and then I can
there,
go for
yeah.
modeling and simulation.
So there's a specific section here, and then here there are um, different. You have the introductory courses, but also some specific. And I think
Yes,
there should be one list here that is,
multi-body
yeah.
modeling and simulation,
So that's
joystick
one
design.
example, and I think there are a few others. And which of these would be the best one for you to start with depends a bit on where you're coming from. Um, but yeah, so probably the one that Ankit showed there is a good starting place after you when you start with the multibody itself. Okay, let's see here, and keep coming with questions if you have any more questions. Uh, Other components which may help model the effects of EM wave on the polarization of air molecules. Not built in, and I don't know if there's any third party. This is completely outside the scope of what I typically do. So I don't know. There are third party libraries that might do this. I don't know any, but I can't say that it doesn't exist. I just can say that I don't know if there is.
But that
To,
that that
yeah,
that brings to a question, Jan. Like, can people use only libraries available in our library store, or can people use other libraries? Like, where can people
yeah.
find libraries?
Yeah, of course. There's a lot of so this uses the Modelica technology, and there's a lot of libraries. Some of them some of them are current, updated, others not. So you have to find the robust, good libraries, and then you can try those. And that's GitHub, things like that. You might find additional libraries, um, and um, and of course, if you have developed the library, you can also share that with other users. By
right?
the way, I don't know if you mentioned that when I was reading, when you were presenting the control design part, I was reading the question, so I missed if you pointed out that what we were looking at was a cloud notebook.
Oh,
Perhaps you did that.
yes. So
Perhaps you did
what
that.
we are, what, okay, yes. So what we are looking here is a cloud notebook. So, so you have system modeling in the cloud as well. You don't have the graphical interface, but let's say you have created a model. So what I have done here is I've just imported the model into my cloud notebook, and then I am using the system modeling functionalities present in Mathematica to play around with how can I check my diagrams, how can I do change a parameter and simulate all those things again. So yeah, you
Yeah.
can if you want to test your models and want to share it with others, then you can use the cloud interface as well.
Right, and here we got some help from a user regarding the previous question, and it says, I think these are 3D PDEs, partial differential equations, and then he asks, does Modelica handle more than 1D? If it's a PDE problem, then that's something that you could do in the Wolfram language, but the SystemModeler and the Modelica language the SystemModeler uses does not support that. SystemModeler is used for the thing that is called 0D by some, 1D by others. I'm on the 1D side. I don't know what you are, Ankit. Um, Hopefully you're on the 1D side too. But basically, things that have where you're not looking into the fine-grained details in space. One could say you're more focused on what happens over time, things that can be described by differential equations. That said, there are people doing some PDE modeling using Modelica, but that's really tweaking it and stretching it. It's not what it's intended for. Yeah,
Right.
and yeah, I see. Yeah, you brought up here
Uh,
here a bit. What is
because
Modelica? If you want to learn a bit more about Modelica, these are really good resources. So yeah,
yes,
I'll get.
and also when we got this question about where can I learn about multi-body modeling, like when you have those kind of questions, it's a very our resources section is a very nice section to go and have a quick overview and try to search for things. Like one thing I wanted to mention was this book. We have this computer modeling and simulation book that also has some chapters on multi-body modeling. So that could also be relevant if you want to learn about it. But in general, we also have recordings, like we have had study groups in the past, and in this page you can based on your interest, these are all 1 hour interactive sessions that we have had before, and you can watch this recordings. Uh, there are many who have found this useful, and as Sian said, uh, system model is based upon the Modelica technology. And if you are new to this term, then we have a nice what is Modelica page where with nice videos, which gives you a good understanding of the technology that our tool is based on. So, but in short, our resources page, I feel, is a very good resource to start browsing for materials. Yeah.
Thanks. Yes, and I think we're running out of time from the time we were given here. So, if somebody has a very fast last question, we might answer that. Uh, Otherwise, I think we're about to wrap it up, and hope the flight was not too bumpy for you guys, and that you got some interesting information. If there are questions you still have, you can of course join that community post and add more questions there, and we try to answer them to that. Would you like to add anything more, Ankit?
Yes, I have the final slide of my presentation left.
Yeah,
No,
that's right.
no, yeah. So
Yeah.
basically, if you are from like the presentation notebooks, you can find it in the community post where we have links to our examples section. So if you are coming from a particular domain and you want to look into specific examples from your domain, our examples page is a nice place to start with. Uh, I showed you the What's New page, but as Jan mentioned, the Wolfram U page is a very nice place to learn different math things related to mathematics and system modeler. But the thing that I like the most is the Wolfram, if is the Wolfram community, and we have our system modeler forum there. So if you have any questions or you might search for answers here, because there are like 311 discussions and maybe some questions people have already answered for you. So it's a nice place to look for past answers and also ask new questions. So I highly recommend you guys to, if you have any questions, please join this group and uh, post your questions here. Yeah, that was it from my side, Jan.
Yeah, then thanks everyone, and me and Ankit wish you a good continuation of your journey.
Thank you.
Thank you.